conic sections in polar coordinates. Okay, so here's the idea, and these two set of directions basically tell you everything that you need to know. But let me just kind of show you how this works. Let's take a parabola, for example. Okay. Now the eccentricity, we've talked about eccentricity before. But basically, here's how it works. Every conic section, there's an associated focus and a directrix. Okay, so let's take the parabola, for example. Okay, that's what I want to focus on, the parabola. And for these equations here, we have the focus at the origin right here. So the focus is right here. The focus is right there. And then here we're going to put the directrix over here. And for a parabola, it's defined, and then it's defined to be the set of points that are equidistant from the focus and the directrix. Okay, so this point right here, so this point right here, that's halfway between, that is going to be on the parabola. Oh man, okay, this is not working out too well. And as you come over here like this, it's going to be more like that. Okay, so if you look at these two distances right here, they're going to be the same. Those two distances the same. Now, this one right here is going to be the square root of x squared plus y squared. That's the distance from the focus to here. Okay, and this is the point x, y, right there on the parabola. And this distance here is going to be, okay, so if this is 0 right here, this is when x equals 0. This is when x equals x equals d. Okay, so this distance is going to be d minus x. Okay, so you basically get that. Now, this is also, when you switch to polar coordinates, this is r, your radius. Okay, because radius is the square root of x squared plus y squared, and d is right there. And this one here is r cosine theta, because that's what x is. Okay, and so you're going to take this to the left side. So you've got r plus r cosine theta equals d, and then you factor an r out, and then you divide by r. You divide by 1 plus cosine theta, like that. Okay, and so then, as you can see, this equation right here, since E is 1, then this is ED over 1 plus cosine theta, or 1 plus, I guess I should say, oh, where's the undo button? They've taken away my undo button. Okay, so I see this update is not that great. Maybe Control Z will do it. No, Control Z doesn't work. It's all those guys. Oh, they made that really huge. Dang, I'm gonna have to look for something else. Okay, so 1 plus E cosine theta. So there we go, right there. And so essentially, this example right here is this one right here. And so it's this case right here, where E is 1. And it's the plus, not the minus one. Okay, so the way that you read that is D is where the directrix is located. Here, it's plus. Okay, so plus and cosine is where the directrix is at x equals D. Okay. Now, if the directrix had been over here, okay, then, wait a minute. Okay, if the directrix had been over here, then it would be minus n cosine, so it would be 1 minus e cosine theta. Now, if the directrix is up here, then it's plus, it'll be plus sine. Okay, it'll be plus sine instead of the plus cosine. And if the directrix is down here, then it's minus sine, or minus e sine theta. Okay, so just depending where the directrix is. Okay, so that's kind of how that works. Okay, so plus and cosine is x minus d. Minus and cosine is x minus d, and so on. And e greater than 1 is hyperbola. So that means that your distance from the focus to the point, any point on a hyperbola, is equal to the distance from that point to the directrix times e. Okay. So those are different. They differ by it. So this ratio is is e for the points, and then for the ellipse, e is between 0 and 1. And just for completion's sake, e equals 0 is a circle. Okay. So, dang, where's the save button? Okay, this is being really bad. Hold on a second. Oh no. What did they do to this thing? I guess it just automatically saves. Okay, so oh, there's the. I have to go out of this and do the undo button. Okay. Okay, so let's move on down here. Okay, so this right here, this instructions right here pertains to the first bunch of problems, and then we have another set of instructions for the last part of the problem. So we'll get to that later. There's just one example. So now let's look at number 1, and I've copied down everything right here. You guys can see this, right? You can.
Yeah.
Okay, good. Okay, so let's see. This set of write it. So number 1 from the exercises, write a polar equation of a conic with the focus at the origin and the given data. So it's an ellipse. The eccentricity is 1/5, which we know it's got to be an ellipse if it's between 0 and 1. So if it's 1/5, it's an ellipse anyways. So that's kind of redundant. This is kind of redundant right here. And the directrix says that x equals 6. Okay. So since the directrix is x equals 6, then we are in this case right here. So it's plus and the cosine. And also, d is going to be 6. So that's the information that we have. And because the focus is the origin. So the equation is going to be, and then here e is 1/5. So we go by this equation right here, ed over 1 plus e cosine theta. Okay, so that's the one that we're going to go with. And so e is 1/5, d is 6, and it's 1 plus, and again, e is 1/5 again right here. And just multiply the numerator and the denominator by 5. And you have 6 over 5 plus cosine theta. Okay, make sure you write it as r equals. Okay, any questions about that? Let's move on to number 2. So here we have write a polar equation with the focus at the origin and the given data. So it's a parabola. Okay, so parabola means that E is 1. Directrix right here, that means D is still going to be 8, positive 8, okay? That's going to be 8. But what this negative does is it's this case right here, see? So that means we're minus and cosine. One minus E cosine theta. Okay, so we'll go ahead and put everything in. E is 1, D is 8, so that's 8 over 1 minus cosine theta. Okay, and make sure you write the R equals as well. Okay, just let me know if there's any questions as we're doing these. Okay,
I have a quick question real quick. The directrix is x equals -8. Why was it d equals 8 again?
Why would it be 8 instead of -8?
Yeah.
Okay, so d is the distance from the focus to the directrix. So.
Okay. And is d always going to end up being positive?
Yes, d is always going to be positive. What does change is this right here. This becomes negative when it's minus.
Okay.
Yes, that's always going to be positive. Okay, so let's go down to number 3. Here we have a hyperbola. The eccentricity is, let's use a different color. So the eccentricity, E, is 4.5. D is going to be 2. But this is Y though, okay? So that means we're in this case right here. So use the plus on the sign. Okay, so we plug everything in. So 4.5 times 2 over 1 plus 4.5. Oh, man. It's got a lot harder. 4.5 sine theta. Okay, because plus and sine. So plus and sine right there. And I can just multiply these out. It will, okay, the way that I put the answer in, it did allow me to just write this way. Okay, let's move on to number 4. Okay, so with number 4, it's more of the same. In this case, this time we're given the equation right here. And so you compare that with R equals ED over 1 plus E sine theta, because it's a plus and sine, right? So yeah, so it's plus and sine is the directrix is going to be Y equals D, right? Okay, and then this is the form. So ED over 1 plus E sine theta. Okay, so we have to try to get, so the key right here is to get a 1 right here. Okay, and you can do that by just multiplying the numerator and denominator by 1/4. So the numerator is going to have a 1/4 here, and then this is going to be 1 plus 1/4 sine theta. Okay, and so that's telling you that E is going to be 1/4. And it's between 0 and 1, so that means it's going to be an ellipse. Okay, because once again, let me go up, let me scroll up a little bit. So E is 1/4, and that means ellipse. Okay, between 0 and 1 is an ellipse. So we know that's an ellipse. And, oh, I have the equations right here as well. Okay. And we know that E times D is but we know that E is 1/4, right? So that means D is 1. So that means the directrix, what the heck? What the heck? Okay, so the directrix is, okay, so this is sine. So the directrix is going to be y equals 1. Okay, because it's plus and it's sine. So sine is the y equals the directrix, and then plus is plus positive d. Minus here would be minus d. So y equals 1. So your directrix is going to be up here. So so that would be like that or that one. Okay. And so, but not so the could throw both of those out. We also know that it is not a parabola, it's an ellipse. So throw that out. It's got to be this one here. Oh, and the directrix, okay, this is the equation of the directrix. So y equals 1 is the equation of the directrix. Now this looks really much like a circle. That's because 1/4 is really small. Okay, so let's move on. So that's all the aspects right there, I guess. Number 5. Okay, so this one, number 5, we're going to compare this with this one here with a minus there. So the key is to make this a 1. So the numerator is 6/5, and the denominator is 1 minus, okay, 20 divided by 5 is 4. So that means that the eccentricity is 4, which means hyperbola, since E is greater than 1. Since the eccentricity is greater than 1, it's going to be a hyperbola. So a hyperbola would be the answer right here. Okay, for the directrix, we know that the eccentricity times D is going to be 6/5. Okay, that's from right here, this numerator, and like now right there. So, and we know that the eccentricity is 4, so that's 4D equals 6/5, and we know, so the D is going to be 3/10. Okay, so we have a minus, and cosine. So that means that the directrix sorry for the bad spelling and whatnot. Nothing. So the directrix is x equals negative 3/10. Okay, so I look for the directrix at x equals -3/10. This one right here, this looks like -3/10, -0.3 right here. And so this is the directrix. This line right here. And the focus, of course, is over here. And so the distance, so if you look at this piece right here, so the focus on, let's see, let me do a different color. So if you look at this, oh, come on. Okay, so if you look at this right here, this is telling you that the distance between any point on this ellipse and the focus is equal to the eccentricity, which is 3/10, the distance between the point and the directrix. So here's the directrix. So this distance, wait a minute. What? Okay, so I'm really confused now. The distance, what? Oh wait, E is 4. What am I doing? So E is 4. Okay. Okay, so the distance between any point and the focus, so this distance from say from here, come on. So distance from that point to there, wait a minute, is this distance right here is 4 times this distance from this point to the directrix. Okay. And this distance here is going to be 4 times this distance. Okay, and so on. For all points on the hyperbola. And same thing if you go over to here as well, okay? So this distance right here is going to be 4 times that distance. So this distance from the focus to here is going to be 4 times this distance from from this point to the directrix. Okay, and that's just kind of how it works. And so yeah, this is going to be the correct answer. These ones aren't even there aren't even hyperbolas, and plus you can't have your conic sections can't be intersecting the directrix like this. It just doesn't happen. Okay. So let's go on to number 5, unless there's any questions. Okay, so number 5, we get into the other set of formulas and stuff, the other set of directions. And this is to do with planetary motion. So planets that orbit the sun, and I guess you could also say the same thing about the moon orbiting the Earth. But planets orbiting the sun, they have elliptical orbits. And so like, maybe I should draw a little picture of this. So like, let's say this is the sun here, and you have, the sun is at one of the focuses of the ellipse. And then you have the planet orbiting like this, okay, in the form of an ellipse. And this distance right here is along the long side of the ellipse is called the major axis, okay? So the major axis would be this right here from here to here. Would be this distance from here to here. And the semi-major axis would be half of that. Okay, so semi-major would be half of the major axis. Okay, now, planets have two positions that we're going to talk about here. Perihelion is the closest to the sun, and aphelion is the furthest away. Okay, so perihelion would be when it's right here. What the heck? And then, holy smokes, oh, I see. I can move stuff around. Oh, great, I can move stuff around though. And then aphelion would be right here. So, can you guys hear the weed walking? They do this every day, like about this time, when we're halfway through the class. Okay, so, and then this is the revised formula. So instead of the numerator being ED up here, it's A times 1 minus E squared. Okay, and then, but this is still E right here, 1 plus E cosine theta. Okay, so let's talk about Mars. So orbit of Mars is an ellipse with eccentricity 0.093. So this is really small. So it looks kind of like a circle. Looks like circular, right? Oh, come on. Okay, and the semi-major axis is 2.28 times 10 to the 8. So that's A right here. Okay, so find a polar equation for the orbit. So you just do this right here. Okay, so I just plug in the A, that's 2.28 times 10 to the 8th, that's our A. And then 1 minus E squared, so 0.093 squared. And that's all over 1 plus 0.093 cosine theta. Okay, and so that's going to be the equation. We can simplify that. That simplifies down to, so if we multiply that times all that, evaluate all this, okay, I did it on the calculator, and that's approximately 2.26028, a bunch of other stuff, times 10 to the, also 10 to the 8th. There's 10 to the 8th right there. So, and it says rounded off to 2 decimal places or 3 decimal places. I made a mistake. 0. Come on. Seriously? You're gonna just play games with me. What the? It won't let me. It's good for nothing thing. Okay, let's delete that. Ah! Okay, 0.093 cosine theta. Okay, so that should work right there. Any questions about that? so planetary motion is fun to do. Okay, let's look at a comet. Now, a comet's going to have much bigger eccentricity. So this is eccentricity 0.9951. Because comets are like, they go a long ways. They go pretty far away from the sun. And then sometimes they come around and they're close every what, a whole bunch of years. Okay, so comet Hale-Bopp or Haley-Bopp, I don't know how to pronounce that, discovered in 1995, has an elliptical orbit with eccentricity. Yay, there's that word. So this is a bigger eccentricity. .9951. I'm trying to just like do a dot there. Oh, well, 0.9951. Okay, the length of the orbit's major axis is 356.6 astronomical units. I think 1 astronomical unit would be, oh dang, I forgot. Is that the distance between the Earth and the Sun, or what? I forgot. Okay, it's something like that. Okay. So, but anyways, 356.6 astronomical units. Okay, so that it's the major axis. So that means that the minor axis would be half of that, because of this. This is semi-major axis. So A is going to be not the minor axis, the semi-major axis. That's half of the major axis. Would be half of that, which is 178.3. Oh, that's a 6. Okay, so 178.3 would be A. So E is that, A is that. Find a polar equation. So that's going to be R equals, so it's A. So you just use this formula here. So 178.3 times 1 minus 0.9951 squared, all over 1 plus 0.9951 cosine theta. Okay, and then if you evaluate everything in the numerator, I have 1.743. Okay, and then the next is 0.59, but you round it off to 4 decimal places right there, over 1. So that means that your equation will be this right here. R equals that. Okay, so how close to the sun does it come? And that's going to be perihelion. So that's 178.3 times 1 minus 0.9951. And that works out to be approximately 0.8737. 87367 is what I got. More precise, they just round, but you got to round this up to a 7 here. Okay, so it looks like it. If the astronomical unit, if I'm correct, if the astronomical unit is the distance between the, I guess I could look it up. If I'm not like astronomical unit. Well, it's the mean distance from the center of this Earth to the center of the sun. Okay, I was correct. Yay. It's basically the distance between the Earth and the sun. It's the mean distance, because the distance varies, of course, because the Earth has an elliptical orbit.